Hello students, welcome back to the classroom point. In our previous class, we have discussed the dynamic equilibrium in the physical process. Now in today's class, we shall discuss the dynamic equilibrium in the chemical reactions as well as how to draw the equilibrium graphs versus concentration versus the time. So let's begin the class. So dynamic equilibrium in the chemical reactions, we can discuss this particular part by taking an example of the preparation of ammonia by Haber's process. So Haber conducted an experiment in which nitrogen and hydrogens are allowed to react with each other, and they reached the equilibrium state forming the ammonia. And Haber was successful in calculating the concentration of the ammonia and hydrogen at the equilibrium stage. Every time when he observes that there is no change in the concentration of ammonia for the provided moles of the reactant and product, that means for constant number of moles of the nitrogen and hydrogen if we take, then the concentration of ammonia and hydrogen do not change after a certain time. Then he thought that the reaction reached the state of equilibrium, but doesn't know whether the reaction is in the dynamic process or not. Already we discussed the meaning of the dynamic process means forward reaction and backward reaction continuously to takes place even at this stage of the equilibrium. That's why he has taken another reaction where nitrogen is allowed to react with deuterium to get the deuterated ammonia. So in this case also, by using the isotope, there is no change in the concentration of the deuterated ammonia once state of equilibrium is attained. Then what he did was, he mixed both of these. Ammonia formation using the hydrogen and a deuterated ammonia formation using the deuterium, whatever these two reactions was mixed, then he observed that what we are expecting is there should not be change in the concentration of ammonia as well as the deuterated ammonia. But in reality, the concentrations do not change, but the chemical formulas are changed. That means after reaction mixture, when you are expecting the only ammonia and deuterated ammonia along with these chemical substances, but other chemical substance also obtained using the deuterium. That means hydrogen obtained as it is, deuterium also obtained, and these two combination gives HD, deuterated hydrogen, and ammonia was observed, and ND3 also observed. Along with that, every time this one of the hydrogen atom is replaced by the deuterium, providing that NH2D, NHD2 also obtained. The question is about ammonia, deuterated ammonia, deuterium and hydrogen. This we can expect because we have taken these reactant molecules and products are formed. But how could these deuterated hydrogen and deuterium substituted normal ammonia, how these three molecules are obtained? This is possible every time when ammonia is converting back into the hydrogen and hydrogen again converting back into the ammonia. So when ammonia molecules decompose and producing the nitrogen and hydrogen, when they again react with each other, there is a chance for this NH3 molecule formation by mixing with not only with hydrogen but also with deuterium. That's why some of the hydrogen atoms and deuterium atoms also included in the normal ammonia molecule to provide the deuterium substituted ammonia. That means the reaction is not stopped. In this case also, deuterium is, every time deuterium is replaced by the hydrogen and giving this type of the combination. So from this it is very clear that the reaction is not stopped even at the state of the equilibrium. Both of the reactions continuously to takes place. So it is proved that the chemical reactions after obtaining the state of equilibrium, there is a movement towards the forward and backward reaction. So we can call such such type of reactions are dynamic equilibrium reactions. Now, let us try to see how to draw the graphs by taking the three general examples. Let us imagine a reaction A is equilibrium with AB equilibrium with C plus D. Here A and B are reactants, C and D are products. So when you start the reaction by taking only reactant molecules, initially there is no product molecules. Then with the time, the concentration of reactants gradually decrease and concentration of the products gradually increase because reactant molecules start converting into the product molecules. So that here we can write down the graph y-axis and x-axis. Let us take the concentration term on the y-axis and the time on the x-axis. So initially products concentration is 0, but reactant molecules concentration is highest. When time passes, the concentration of reactants decreases and concentration of the products gradually increase. So concentration of the products gradually increases, and after certain time there shall be no change in the concentration of the products, so they remain same. At the same time here, concentration of the reactants gradually decreases, and after certain time again they remain constant. That means from this particular state onwards, the concentration of the products, this is the concentration of the products and this is the concentration of the reactants. Concentration of the reactants, there is no change. Concentration of the products also, there is no change. That means we can say that the reaction reached the state of equilibrium. So this is called the equilibrium state. So if you observe this particular graph, it is saying that after equilibrium, products concentration is higher than the concentration of the reactants. It is not always correct. Only for this general example, we are taking like this. In many reactions, it may not follow. Let us take another example. Let us take the formation of ammonia. In Haber's process by the reaction of nitrogen with hydrogen. So when you observe the graph of this one, concentrations on y-axis and time on x-axis 0. So it was observed that the concentration of ammonia gradually increases and remains constant after certain point. And between the nitrogen and hydrogen moles are more than the nitrogen, so that we take from here. So its concentration gradually decreases and remains constant after certain time. Nitrogen, its concentration also decreases and remains constant after certain time. So this is about the concentration of ammonia. This is the concentration of nitrogen, and this is the concentration of hydrogen. If you observe in this case, from this particular point onwards, there is no change in the concentration of the either reactants or products, so that we can say that the reaction attained the state of equilibrium. So in the state of equilibrium here, which concentrations are higher? See here, concentration of hydrogen is greater than the concentration of nitrogen, is greater than the concentration of ammonia once the reaction reached the state of equilibrium. So this is completely different from this one. So we can say that always the concentrations of reactants are not less than the concentration of the products for any equilibrium. It depends on the type of reaction what we select. Let us pick up another example. Formation of hydrogen iodide from H2 and I2. And when you observe this, the 1 mole of H2 reacts with 1 mole of I2 and giving the 2 moles of hydrogen hydroiodic acid. That means number of moles of hydroiodic acid is more than the H2 and I2, and this reaction we can take by taking we can achieve by taking either HI molecule or H2 and I2 molecule, because equilibriums can be achieved by taking the either reactants or products. Now let us try to get the graph for this one. Concentration, here concentration, and this is time. So the left side says that we begin with H2 and I2, and the right side says that we can achieve the reaction by taking the HI molecule. So imagine H2 and I2 molecules concentration, because both are equal, so that both begins from here only. With the time passes, their concentration gradually decreases, and after certain time they remain constant. If you begin the same reaction with HI, number of moles of HI is more than the both H2 and I2 individually, so that it has to begin from here point, because concentration is higher. So when time passes, the concentration of HI molecule gradually decreases and reaches the state of equilibrium after certain time. And if you completely come this side, that means HI molecule completely convert into the H2 and I2, so that finally you can see that here HI molecule concentration is 0, because only H2 and I2 molecules are present here. And if you extend this particular graph, and you will get point 0, that means H2 and I2 becomes 0 at this particular point, because here only HI lies. Then if you observe this particular point from this area to this area, these are all horizontal lines. That means the concentration of HI and concentration of H2 and I2 do not change. So this area is called as the equilibrium state. We can say that the system achieved the state of equilibrium, and this is saying the concentration of H2 and the concentration of I2. This is saying the concentration of HI. And in this particular process, you can observe that concentration of HI at equilibrium stage is higher than the concentration of H2 and I2 for this particular process. So we can write down that concentration of H2 and I2 less than concentration of HI at equilibrium stage. And these concentrations may change depending on the conditions what you take. Here normal conditions at room temperature are given experimental condition, these are obtained. But once you apply the more pressure, temperature conditions according to Le Chatelier principle, these concentrations varies, so that only graphical representation gives this idea. Dear students, I hope you understand today's class. We shall meet in the next class. Thank you one and all.